When you ask an AI to generate an image, how does it actually create something out of nothing? A common misconception is that it pieces together a collage of images it has seen before. But modern generative AI doesn't build an image piece by piece. Instead, it sculpts it out of pure static. It does this using a diffusion model, a system that learns to create by first mastering the art of destruction. To teach a model to denoise, we first need a forward process, denoted as Q. We take a clean image, x0, and gradually add Gaussian noise over t time steps, usually 1,000 steps, until it becomes pure static, xt. But stepping through this one by one during training would be incredibly slow. Thanks to a mathematical shortcut called the reparameterization trick, we don't have to. By defining a noise schedule, alpha, we can calculate the exact state of the image at any arbitrary time step t in a single jump. We just scale down the original image and scale up a random noise vector, epsilon, and add them together. Now for the reverse process. We train a neural network to undo this damage. But here is the crucial part. The network doesn't try to predict the final clean image. That's too hard. Instead, it looks at the noisy image, xt, and tries to predict only the noise, epsilon, that was just added to it. We take the actual noise we injected during our fast-forward step and compare it to the noise the network guessed. We calculate the mean squared error between them and update the network. This simplified loss function is incredibly stable, avoiding the mode collapse issues that plague other generative models like GANs. The engine doing this work is usually a U-net. It first compresses the noisy image down to extract deep semantic features and then expands it back to its original size. To prevent losing fine details during this squeeze, skip connections bridge the high-resolution data directly from the encoder to the decoder. But the U-net needs one more critical piece of information. What time is it? Because the noise characteristics change drastically from step 1 to step 1000, we inject a timestep embedding into the network. This acts like a clock, telling the U-net exactly how much noise it should expect to find. Running a massive U-net on a high-resolution image 1,000 times is computationally brutal. To solve this, models like Stable Diffusion use latent diffusion. Instead of adding noise to a 512 by 512 pixel image, they first compress the image into a tiny 64 by 64 mathematical representation called a latent space. The entire diffusion process happens in this miniature space, making it exponentially faster. Furthermore, researchers optimize how the noise is added using a cosine schedule. Instead of adding noise linearly, which destroys the image too fast, a cosine schedule decays the signal smoothly, preserving structure longer and making the network's job easier. To summarize, diffusion models work in two phases. During training, we take a clean image, use the reparameterization trick to instantly jump to a random noisy state, and train a U-net to predict the exact noise we added using a simple mean squared error loss. During generation, we start with pure random noise. We feed it into our trained U-net, ask it to predict the noise, subtract a fraction of that noise, and repeat the process. Step by step, the model carves away the static, revealing a perfectly synthesized image from the latent space.